Hello, grade 12s. Let's continue with question 11 of Euclidean Geometry pre-June exam 2025. So let us look at question 11. They are saying in the diagram, LK is a diameter of a circle with center P. So when they give you the diameter of a circle, you should look for the angle which is 90 degrees. You look for the angle which is subtended by the diameter. So let us look at the diameter LK in the diagram. So we've got a straight line from L. Now this straight line from L passes this. Yes, is it P the center? Oh, yes, P is the center. Pass at the center P. So this is my diameter LK. So I'm going to look for the angle which is subtended by the diameter. I know that the angle subtended by the diameter is 90 degrees. So whenever they give you the diameter, you look for the angle subtended by the diameter. So I have L K, which is my diameter. So which angle is subtended by the diameter? I'm going to draw a line from L, draw a line from K. I'm meeting at N2, which means that the angle N2 is 90 degrees. This is what we call the angle subtended by the diameter, or what we call the angle in the semicircle. So please, grade 12, whenever they give you the diameter, you have to look for the angle in the semicircle. In this case, the angle in the semicircle is 90 degrees. This is the angle subtended by the diameter. Okay. In the diagram, LK is the diameter of a circle with center P. And another thing that you have to check, once they give you the center, you look for the angle at the center theorem. This time around, it won't apply. I don't see it applying. Now they are saying R and S is a tangent. So let me pull it a bit up. R and S is a tangent. So we've got the line of tangent, which is the line R and S. So it means that this line of tangent touches the circle only at a point N. Remember, tangent must touch the circle at one point. So they are saying the line R and S is a tangent. And I told you that whenever they give you the tangent, you have to check how can you apply the tan chord theorem. So I have to identify my chord. So what is my chord? My chord is NR. NR is my chord, which means that the angle N3 is the angle between the tangent and the chord. And what do we know about the angle between the tangent and the chord? It is equals to the angle in the other segment. How do you find that angle in the other segment? You use your chord. You subtend your chord. So let us look at the chord NK. You look at this chord NK, you use it now, you subtend this chord NK, you see that, okay, from N and from K, we meet at L. From N, from K, we meet at L. So it means that this angle N3 is equals to the angle L. This is tan chord theorem. So once they give you tangent, look out for the tan chord theorem. N3 equals to L tan chord. Actually, it is a good idea in Euclidean geometry not to rush in answering the questions. What you should do, you go through the diagram, you interpret the diagram. You look for the angles that are equal. Why are they equal? N3 equals to L due to the tan chord theorem. And if you apply tan chord theorem, you will also see that the angle N1 is equals to the angle K. So you write down this information. N1 equals to K tan chord. Before you rush into answering the problem, okay? Another thing we are told that TP is perpendicular to KL. Two lines are perpendicular. At the point of contact, they must form 90 degrees. So they are saying TP is perpendicular to KL. Let us look at TP. Okay, this is my TP, which they are saying it is perpendicular to KL, is perpendicular to this line, which means that at the point of contact, whenever perpendicular lines meet, they form 90 degrees. So this angle here is 90 degrees, and which means that also the angle this side is 90 degrees according to the angles on a straight line. Okay, let me do this, and 3 I know equals to L, and then you'll be having a highlighter. It's important to highlight the angles that are equal, and 1 equals to K. Okay, so I think now we are ready to answer the questions. So let's hear what they want. The first question say, prove that TPLN is a cyclic quadrilateral. Okay, normally there are three ways in which we prove that a quadrilateral is a cyclic quadrilateral. So let us look at the quadrilateral which they are talking about. They are talking about the quadrilateral TPLN. TPLN. They are talking about this quadrilateral TPLN. So they are saying we should prove that this quadrilateral is a cyclic quad. Okay, we know that opposite angles of a cyclic quad are supplementary. I'm going to use this theorem about a cyclic quad that says opposite angles of a cyclic quad are supplementary. So we already know that this angle is 90. I just have to check how can N2 be 90? Because this P and N2, these are the opposite angles. And in a cyclic quad, opposite angles must add to 180 degrees. So let me say I give you a quadrilateral, guys. Let me say I give you a quadrilateral A, B, C, D. And I tell you that B, it's 120. D, it's 60. Automatically, A, B, C, D becomes a cyclic quad. Why do we say it's a cyclic quad? Because we see that opposite angles add to 180. So whenever we give you a quadrilateral whereby opposite angles add to 180, that quadrilateral is a cyclic quad. So here, if you look at this quadrilateral that which they are talking about, TPLN, this angle here is 90 degrees. So for this TPLN to be a cyclic quad, even the angle N2 must be 90 degrees so that we can say opposite angles add to 180. What do we know about N2? We know that the angle N2, it is the angle in the semicircle, or it is the angle subtended by the diameter. What is my diameter? I have got L, I have got K. This LK is the diameter. So I look for the angle subtended by LK. So I move from L, I move from K. So the angle subtended by LK is this angle N2. So you say N2 equals to 90 degrees. Why is N2 90 degrees? You can say angle in the semicircle, or you can call it angle subtended by the diameter. Now, because we see that N2 plus this angle P here, this angle here, let me just call it TPL. N2 plus TPL, we see that it's 180, which is 90 plus 90, equals to 180. So we can now say this quadrilateral TPLN, therefore TPLN is a cyclic quad. This is a cyclic quad. Why? From the converse of the theorem that says opposite angles of a cyclic quad, opposite angles of a cyclic quad are supplementary. So all the time, whenever the opposite angles add to 180 degrees, it means that quadrilateral is a cyclic quad. So in this case, this angle P, it's 90. This angle N2, it's 90. So it means this quadrilateral, it's a cyclic quad. So let me give you the advice. Immediately you finish to prove that this TPLN is a cyclic quad, you automatically now look for additional the additional information which comes as a result of your proof, because you have proven that TPLN is a cyclic quad. You can automatically say the angle LT2 is equals to the angle X. And you can now also say the angle, this one, P, which is this one outside here, is equals to N2. I'm going to explain why am I saying this. Okay, why am I saying T2 equals to L? Remember, we said this is a cyclic quad. We said this is a cyclic quad. And what do we know about a cyclic quad? We know that the angle outside the cyclic quad, the exterior angle of a cyclic quad, is equals to the opposite interior angle. So the angle outside the cyclic quad is equals to the opposite interior angle. So you have to take this into account, because you have proven that your quadrilateral is a cyclic quad. So you have to get more information now. There is information that comes as a result of your quadrilateral being a cyclic quad. Because we found that the quadrilateral is a cyclic quad, we know that the exterior angle of a cyclic quad equals to the opposite interior angle. So my advice is, immediately you finish proving that a quadrilateral is a cyclic quad, do not rush into answering other questions. Don't move. automatically now look for the angles that becomes equal just because the quadrilateral is a cyclic quad. So, okay, what I'm saying here is that the angle T2 becomes equivalent to the angle S, which means that actually T2 is X. But if you rush, you won't see that. Okay, so we have proven that this is a cyclic quad. Now let's continue. Determine, given reason, the size of N1 in terms of X. They are looking for the angle N1 in terms of X. When we say, give us your answer in terms of X, we are saying in your answer, X must be there. Maybe you can get 2X, 3X, 4X, or 180 minus X. In your answer, X must be there. We are looking for N1 in terms of X. Okay? So let's see how can we find this N1 in terms of X. What do we know about the angle N1? Maybe this is a very valid question that we can ask ourselves. What do we know about the angle N1? We know that the angle N1 is equals to the angle K. What is the reason? Tan-Cot theorem. I told you that the angle between the tangent and the chord is equals to the angle in the other segment. And how do you find the angle in the other segment? I said use your chord. So what is your chord? Your chord is NL in this case. So you subtend your chord, you move from N, you move from L, you meet at K. So you see that N1 is equals to K. This is what we know about N1, Tan-Cot. This is what we know about N1, Tan-Cot. So N1 equals to K. What else do we know? Okay, remember they want us to find N1 in terms of X. And we already found this angle to be 90 degrees. This angle was already found to be 90 degrees, which means that now I can find K so easy. And once I find K, I found N1 because I said N1 is equals to K. So let us find K. We are going to use the sum of the angles in a triangle L and K. I'm going to say angle L plus N2, which is 90 degrees, plus angle K is 180. So L is X, N2 is 90, plus K is equals to 180. Now you want to solve for K. K is equals to, you take 90 to the other side. You take X to the other side. You are transposing. So angle K is equals to 180 minus 90 minus X, which means that angle K is 90 minus X. Therefore, N1 is equals to 90 minus X. So you found N1 in terms of X. That's what they wanted. 3 marks. Do not forget to provide the reasons, guys, why you say N1 is 90 minus X. Now they say we must prove that the triangle KTP, I'm reading 11.3.1, prove that the triangle KTP is similar to the triangle KLN. KTP it's similar to KLN. Okay, KTP, it's similar to KLN. Let me confirm that. Okay, let me raise it. I want to confirm the question for the last time. Prove that KTP is similar. Yes, KTP is similar to KLN. Proving the similarity of triangles. How do we prove that two triangles are similar? Most of the time we use the angles. So prove that we need KTP, prove that triangle KTP is similar to triangle KLN. So proving the similarity of angles, proving the similarity of two triangles, we use the angles most of the time. So what I'm going to do, I'm going to say, okay, for these triangles to be similar, the angle K from triangle KTP. So actually, let us go and look for this angle K in the triangle KTP. This is the K in the triangle K, in this triangle. Actually, this is the triangle which we want to prove that it's similar to the triangle KLN. Where is KLN? KLN. So these are the two triangles that I want to prove that they are similar. The smaller one and this other one, the bigger one. So I want to show that K in triangle KTP is equals to K in triangle KLN. So if you look at K in KTP and K in KLN, you see that this is the same angle K. Is the same. Like if I ask you what is where is angle K in KTP? Look at it. Let me erase this thing. Where is K in KTP? KTP. This is my angle K. Where is angle K in KLN? In KLN, you notice that this is still the same K. This is still the same angle K. So we say the angle K is a common angle. So I will say K from KTP is equals to K from KLN. Don't forget to write the reason, is a common angle. It's a common angle. Now, okay, now I want to show that angle T is equals to angle L. I want to show that angle T in triangle KTP. Where is angle T in triangle KTP? Is this angle T2? Is this angle here? I want to prove that this angle T in KTP is equals to angle L in KLN. So let us go to KLN. Is this angle here? What am I saying? Yes, let us look for L in KLN. Exactly this one. This is L in triangle KLN. And I already told you that these two angles are actually equal. So you say T2, this T in triangle KTP is T2. So T2 is equals to angle L. They are all equals to X. What is our reason here? Exterior angle of a cyclic of a cyclic quad. The angle outside cyclic quad. Do not forget that we have proven that this shape is a cyclic quad. This shape is a cyclic quad. And I told you that the angle outside, the exterior angle of a cyclic quad, is equals to the opposite interior angle. So that's why I'm saying T2 equals to L equals to X. Now, once you have proven that two angles are equal, don't go for the third one. The third one in P in KTP, where is it? Is this one, which is 90 degrees. Don't try to prove it, this one. Just show that you are talking about P in the same triangle and say equals to. Now you go for N in KLN. Where is N in KLN? This N is N2. It's N2. Your reason here is the third angle, third angles of a triangle. You can just say third angle of a triangle. Therefore, the triangle KTP is similar to the triangle KLN. So you just focus on showing us that we have got angles that are equal. This is how you prove similarity of triangles. You just show that we have angles that are equal. So if we say, I'm just summarizing this one, I'm concluding on it. If I say to you, prove that triangle ABC, it's similar to triangle DEF. Your focus is on showing me angles that are equal. An angle A in triangle ABC must be equals to D in triangle DEF. So your focus is going to be on A and D. They must be equal. B and E, they must be equal. C and F, they must be equal. We actually say corresponding angles of similar triangle are equal. This is what we know about similar triangles. Corresponding angles of similar triangle are equal. So in this case, A correspond with D, B correspond with E, C correspond with F, and the corresponding angles of a similar triangle must be equal. So I've proven 11.3.1. So now I have to answer 11.3.2. Okay. 11.3.2. Let me erase. I'm using a wrong eraser. Sorry. Yes. Let me erase. Okay, now I'm answering 11.3.2. To answer 11.3.2, guys, you are going to use the information of 11.3.1. This is what you must not forget. So you are going to say, okay, remember, we have proven that. We have proven that the triangle KTP is similar to the triangle KLN. So what you do this time around, you say KT over, you go and pick the first two that side. KL, you say equals to, you can take the last two, TP, TP, you over, you go and take the last two there again, LN, equals to, you take the first and the last, which is KP, over KN, the first and the last. Now, after writing something like this, you now look where you are going. You want to prove this. So now you are going to pick two of these guys. It's either you pick this one and this one. Okay. So, but you have to look at the information. We have KT times KN, for example. So if I pick this first and pick the last year, I know that when I'm going to do cross multiply, when I multiply KT with Kn, is this part here, KT times Kn. So I'm going to take the first and the last. I'm going to say KT over KL is equals to KP over Kn. And I must write the reason. What is the reason? This is the corresponding sides of similar triangles. We know that the corresponding sides of similar triangles are proportional. So that is why we say KT over KL equals to KP over KN. Corresponding sides of similar triangle are proportional. Now, if we do cross multiply, we have KT times KN. I want to write it here. KT times Kn equals to, cross multiply, I have KL times KP. KL times KP. Yes, I want the diagram. Now what I'm going to do, I'm going to say, I wish we see where we are going. It's always important. Let me write what we are proving this side. This is the final end. It's where we are going. Let me show you where I take it from. This is the answer that we want. We want KT times KN. We're talking about this. We want KT times KN equals to 2KT squared minus 2TP squared. As case I'm running short of space there. Okay, let us look at the diagram. I want us, we see that KL here and KP, we don't need them. They are not here. On the right hand side, we don't have KL and KP. This is where we are, and this is where we are going. So we see where we are going, we don't have KL and KP. So let us look at KP and KL. This is my KP. Okay, and this, the longer one now, it's my KL. Okay, what we notice here is that KP, this KP is equals to LP. These are the radius of a circle. The line from P to the circumference L is a radius. A line from P to the circumference K is a radius. So PK is a radius. PL KL is a radius. So what I'm going to do now, I'm going to say, okay, KT times KN equals to, I'm going to write KL as 2kp. Remember, KL, the distance from K to L, K to L is equivalent to KP plus PL. So the whole distance of KL is made up of two segments. It is KP and PL. So KP plus PL makes KL. So now we can say, okay, KL equals to KP plus this PL also, I can substitute it with KP. Remember, I'm saying KP and PL, they are equal. These are our radius. So I can say, where see PL, I can put KP. So that KL becomes 2kp. So now my KL is 2kp times kp. Show all the workings in your exam. You have to show us why you say KL is 2kp. Now you have KT times KN equals to 2kp squared. Kp times kp. And this kp squared, okay, this kp squared, it is not there on my final answer. If we look at the final answer, we don't have kp here. We only have 2kt squared minus 2tp squared on my right hand side. I don't have this kp. So it means I have to substitute kp, this kp side. What can I substitute kp with? I have to notice that the triangle KPL, it's a right angle triangle, and this side is my hypotenuse, the side which is opposite to 90 degrees, or the longest side on a right angle triangle is your hypotenuse. So we know that hypotenuse squared is equals to the sum of the other side squared. So it's kp squared plus pt squared from the theorem of Pythagoras. Write it in full. Theorem of Pythagoras. Now you make this kp squared the subject of the formula. You say kp squared, it's equivalent to, you take pt squared to the left hand side. So kp squared is equivalent to kt squared minus pt squared. So you say kt, you now come here, kt times kn equals to 2. You substitute your kp squared. You know kp squared, it's kt squared minus pt squared. So you have it kt times kn equals to 2kt squared minus 2pt squared. You have proven. You have proven. This is what they wanted. They wanted you to prove that kt times kn equals to 2. If you look here, equals to kt times kn equals to 2kt squared minus 2 tp squared. Tp is the same as pt. So that is proven. Thank you for visiting Academic World by Mpakela TL. Please subscribe and just comment. Tell me how I can improve on my work. Just share ideas. tell me what is it that you understand, what is it that you don't understand. Okay, just engage with us, academic world, by Mpathala TL, where we love mathematics. Maths, it's one of the interesting subject, guys. So we'll keep doing maths. Yes, we keep doing maths.